Welcome back. So I have a new puzzle to show today and some really incredible mathematics related to it. So this is called the diminished cube, and you'll see it's stickless first of all. That means that I didn't actually build this copy on my own 3D printer. Somebody else actually built this for me. So I sent the designs off to Canyon Cubes, and he's the one who made this copy, the stickerless version. But it's my design, and if you want to buy one, you can find a link to his store and where you can buy this, and I'll get a cut of that down below. So what is going on here? You can think of the shape in a few different ways. One way to think about the shape is take a regular cube and then take these three corners and cut this back corner off on these 3 points. Make a plane there and cut it off, and you have a new face. And then you have to distort the shape. And you distort the shape in such a way that, okay, this face is adjacent to this face, and that face, and they need to be able to interact. So essentially, this turn takes this axis to that face and to that face. So those can all interact. The same for all of the other faces. So this face is adjacent to that face, this face, that face, and that face. So the turning axes for all of those need to move between each other, which is exactly what happens here. So you can see how, one, this will jumble, and two, there are a lot of stored cuts. So you can see several stored cuts built in that are specifically put there so that you can scramble it quite a bit. Let me not get lost. I'm not looking to do a scramble and a solve in this video, but this is the diminished cube. So Canyon did a great job with the print, and I was kind of surprised with the design. It came out one shot. One of the challenges is these faces are fairly extended, so you can see how far these petals stick out. Now, those petals, yeah, they're a little squishy. They don't come out. You can't. They really won't come out. You can move it. I can push on them. They are anchored in there. They're not coming out. So this is the diminished cube, and I want to tell you about some of the math behind this. So we'll do that in the next section. Before we jump there, I'll just say this. The main property that this has, and this shares this with another puzzle I'll show, is every edge has an angle called the dihedral angle. And this shape, and what's nice about this shape is this is the true shape of the puzzle. Every edge on this puzzle has the same dihedral angle. And that's what makes it mix up locally. That's this property here that allows everything to interact. Before I forget, Canyon also sent me this for free, and it's the square one mod. So essentially, it's a square one up top, and on the bottom, it's essentially a 2x2 that starts to bandage up the square one. It's been a long time since I've solved one of these. I need to sit down and figure it out, but it turns very well. So if you buy any puzzles from Canyon, I think you'll be very happy with it. So we have the diminished cube, and here we have the Lich's nemesis. So both of these are inspired by the same idea, and that's the idea that every edge has the same dihedral angle as every other edge on the entire shape. Now, the Lich's nemesis breaks that a little bit. This short edge is a 90-degree angle, and that's not the same as all the others. And then this edge here is not the same as the others. I'll throw up a picture of what the true shape for this is. And you'll see why I didn't make it that shape. Essentially, it's way too long. So I cut this one down and it introduces these new edges. But the main idea is that you get a basic idea for the shape and an axis system that scrambles and will jumble, usually. So there are some caveats. When you have a shape or a polytope or a polyhedra where every edge has the same dihedral. Now, there are all sorts of twisty puzzles that don't have that property. It's not necessary, but it's a really interesting condition that characterizes the idea that as an edge scrambler, if you just look at the edges here, the edges will always interact. So as long as you have the same dihedral around the whole entire shape, if you have an edges only puzzle, it'll scramble, and it does so locally. So there's no like large distances that you have to cover where it's like this axis and this axis have a matching angle, and so on a deeper cut puzzle it'll scramble different. So this idea of matching dihedral angles captures a property of twisty puzzles, and I want to jump into some of the math behind that. So what other shapes have this property? Of course, you have all of your platonic solids. Platonic solids, you have Catalan solids, you have two Archimedean solids that fall into this camp. And you have a lot more. You have bipyramids. Let me put a few more. And you have a whole list. I'm just going to throw up a plot that I put together for various shapes that have a single dihedral angle. And you'll see that I plotted this. In this plot, you'll see on the x-axis, or the bottom axis, is the dihedral angle of all the edges for the shape. And all the dots or the dashes represent a solid that has a single dihedral angle. It's quite a complicated diagram. There are all sorts of shapes that show up, and this is far, far from all of them. In fact, I will try and make another video on this where I show that there are infinitely many, infinite families of these types of solids. And let's throw up a few more shapes that show up. So you have diamond-like shapes. You have some that have like a pyramid on the top and then stacks of antiprisms. In fact, that's a generic way that you can build a lot of these monodihedral solids. So that's a name that we could give them. Mono is in one, and they only have one dihedral angle. So a natural question that you may ask is classification. Is there a classification? For there to be some kind of classification, you need a small amount of them. If you have a continuum of solids, you would have a problem. I mean, it may still be possible, but usually if you want to talk about classifying some sort of discrete structure, you want a countable number at least. And this gets us to an interesting question. Are there continuous families of monodehedrals. And what do I mean by this? Since I can't change the underlying graph, so there's some graph for the shape that will pop up. I'm not changing the underlying graph, but what I can do is I can deform this shape in some continuous fashion to maybe a flatter version. So maybe it's something like this. And let me just throw up a quick GIF showing a slow deformation of a solid here. So it turns out that the answer is no. You cannot have this, and there's a really nice formula that actually implies this fact. And that is Schlafli's formula. So if I have polytope I will have some edges, E. I will have a dihedral angle, so if I have some edge E, then the angle from this face along the inside to that face, I'm going to call theta, is the dihedral angle. And the formula says that if I have a continuous family of polyhedra, let's say x sub t, this is a continuous family, and let's say it's differentiable. Then, if we sum over all the edges, the length of the edge as it changes with time times the derivative of the dihedral angle of the corresponding edge with respect to time, then we always get 0. When I ran across this, I was quite surprised. I have no idea, and initially I had no idea why the heck is this true. But let's see how we can use it first. If I have a solid, let's do a quick sketch, and I can deform it. And I can deform it continuously and let's say differentiably so that theta et, well, if it's monodihedral, it has the same dihedral angle everywhere. At every step in the process, these all have to increase simultaneously. This will also be equal to the dihedral angle for edge number 2 or edge number 1 through time, and they both increase together. Well, if that happens, all of their derivatives are positive. Strictly positive. Lengths are strictly positive, and this sum is strictly positive. It can't be 0. So clearly, just out. It just rules it out. We cannot have a continuous family of deformations. So, cool. Schlafli's formula does it for us. We don't have continuous deformations of monodehedrals. And that tells us one important fact. If we look at all the shapes, so if we look at monodehedrals, and for each one we extract a list of possible dihedral angles. Well, each monodihedral has some combinatorial shape. There's some graph that basically tells you what it is. And since I can't do continuous deformations and get a continuous family of angles that make it monodihedral, I have to have a bunch of, at most, discrete angles. So let's say this is my theta. Maybe it's monodihedral at a couple different places. But it cannot be monodihedral on an entire segment. So for each graph, I have some finite, or at least countable, set of points. A countable set of possible angles for it to be monodihedral. Graphs are countable as well. In fact, well, in particular, planar graphs and polyhedral graphs are countable. So this means that possible dihedrals are countable in size. And that means that our graph that plotted a bunch of different potential dihedral angles, it truly is countable in size. And that's good. That's a good start for classification. We actually know that we can't have a continuum of these things that could make it quite difficult. There's another question that we could ask. Is it actually possible to have multiple angles? Let's answer that in the next part. Do we have one? Do we have two, three, or more? How many dihedral angles can an abstract combinatorial graph achieve where every edge will have that one fixed angle? For that, we need something much stronger than Schlafli's formula. And there is some interesting, let me just call it drama, in the mathematical community. So, can a polyhedral graph be monodihedral with two angles, with two different dihedral angles? And the answer to this is we have no clue. It's not understood yet, but here's what I can say. Several years ago, some collaborators, Wang, Xi, and Yu, claimed that the answer to this is no. And the way that they claimed it in this paper is by proving Gromov's dihedral rigidity conjecture. If you look at the dihedral angles, there's like a little bit at the bottom. The conclusion is that the dihedral angles for these two different metrics are the same. They're basically saying there's no way to have two different angles, sets of dihedral angles, where one set is bigger than the other set at every edge. That's a stronger thing than even what we're asking. They claim to have proven this. And then a few years later, Bear, Hank, and Schick gave a disproof. They gave a counterexample to a part of their paper. And let's go back to the Wang, Xi, and Yu. If you look at the version history at the bottom, they have been trying to fix that. So maybe their approach is on point. Maybe they'll figure it out. Maybe they are right and it hasn't been worked out. But what I can say is it hasn't been peer-reviewed and published in a journal. Don't ask me what I think. I am not an expert in that area. But I did run across one of the recent citations of their paper by Brindle in an Invenciones paper. So it's a really good journal, first of all. So I would go with Brindle's opinion on this. He doesn't really give an opinion, but what he says is he calls their paper a proposed approach. To me, that just reads as it's just not settled. And this person looked to be somewhat of an expert in the field, and they viewed it as an unsettled problem. So I'll take it as unsettled. We don't know. So that's the state of it. So in the next section, we're going to see a really slick proof for Schlafli's formula. I can't take credit for this. The proof that I'm going to show here comes from Craig Hodgson's PhD thesis. So he shared this really slick way to prove it, and in fact, the version he shared is far more general than what I'm sharing here. He proves it in all dimensions, so there's higher dimensions of this, where you look at the areas of faces or the volumes of like hyperfaces, along with the generalization of the dihedral angle. He also proves it for hyperbolic or elliptic geometries where you have different kinds of curvature. I'm cutting that stuff out. We'll keep it simple, we'll avoid curvature, and the way he proves it, so I'll call this Craig Hodgson's proof. He uses a really cool technique called Crofton's Crofton formula. This is the key thing that it uses. But we'll get into that in the next section. Before we'll do that, I'll just remind you of a basic fact for polygons. So polygons, you have a set number of sides, and at each vertex V, we could extend a face, and there's an angle alpha. And so each one of these, let's say alpha 1, alpha 2, alpha 3, alpha 4, and so on and so forth. If we sum up all of the alpha i's, what we get is 2 pi, because we turn, these are the turning angles, we do a full 2 pi rotation. Now, for us, the analog of the dihedral angle is theta here on the inside, which you can see theta is actually pi minus alpha. And so one of the basic formulas that we will need is the following. We'll need, just flipping this around, if we sum up theta I, the dihedral for each one of these, this is really the sum of pi minus alpha I, and then these sum to 2 pi, and then we have a number of edges, so this is the number of edges times pi minus 2 pi, basic formula, maybe you've seen it before. The main thing is this is constant. It's essentially constant with the exception of the number of edges, but in what we're going to do, the number of edges changes instantaneously and then it's constant. And we're going to be taking a derivative of this. Another way of seeing this is that if we take the derivative of both sides, let's say I have a polygon that's changing with time, and I look at the derivative of the sum of the dihedral angles. This is the dihedral angle for a polygon, one dimension down, over time. This is equal to 0. You can see that this already looks like Schlafli's formula because it is one dimension lower. What's the length of a point? It's 1. It's all points are the same. You count the number of points. They're all length 1. There's no length. So actually, we kind of already have the 0 dimension Schlafli formula. Now we need the 1 dimension up Schlafli formula. And what Craig Hodgson did is he used this Crofton formula to actually bump this up a dimension, which is what we'll do in the next section. How do you measure the length of a curve? You might go, if you've taken calculus, let's take a curve gamma. You might go, let me parameterize the curve and let me integrate over the curve. Let's do something different. Let me put down an origin, and an axis system. So our curve lives somewhere. And then I'm going to pick an angle, phi, and a radius, r. And I get a nice little vector here. It's a little small, but I need to have it right there. This defines a line. I can take the line orthogonal to that vector, and we have the line L. And if we look at our line L, this line L goes through our curve gamma twice. So we can define the intersection number of this line L with gamma. So for our curve gamma and for the angle phi and the radius or the distance r, we have 2. Cool. How do we measure length with this? If I told you what the intersection number was for every angle and every radius r, could you tell me how long the curve was? That is Crofton's formula. The length, this is incredible. I love this. The length of gamma is 1/4 the integral of this intersection number in gamma phi r d sub phi d sub r. We integrate over all the lines in the plane, and we integrate the number of intersection points. And we divide it by 4, and we get the length. Why the heck does this work? This is brilliant. I think it's brilliant. I saw this and I was like, I have to incorporate this into a video. Why is this the length? Another way of saying this is a random line. The average intersection number with a random line in the plane tells you the length of your curve. Let's think about how to prove this. And we'll prove it with words. Why? Why is this true? So the first thing to note is this. If I have 2 curves, say gamma 1 and gamma 2, and I look at n of the combination of these 2 curves for some plane, gamma 1 plus gamma 2 of phi r. What's the intersection number? And let's just toss out the midpoint. That happens precisely for like one line, okay, maybe like a one-dimensional subset of lines. It's a single point that might throw things off. It actually doesn't throw things off too much. It throws it off by 0, actually, when you integrate it. What's the intersection number for the line L through the combination of the 2? Well, it's how many times you intersect the first one plus how many times you intersect the second one. Gamma 1, phi r, gamma 2, phi r. So whatever this is, let me call this f of gamma. Whatever it is, f of gamma also has this property. F of gamma 1 plus gamma 2 is f of gamma 1 plus f of gamma 2. That's starting to look a little bit like a length. That's kind of funny. Okay, let's push this a little bit further. Well, since we can concatenate things, if I have a curve, I can approximate my curve arbitrarily well with straight line segments. So my curve might as well be a bunch of very, very short line segments. If it works for line segments, then because I can add them up, and we just observed that if I combine two paths, two arcs, then the formula is the sum of the formula applied to each piece, then it works. For gamma. Okay, so I only need to check this for an individual line segment. So let's say I have my base point here, and then I have some random line segment in space here, and I want to look at this approach here. Does it work for a line segment? Well, here's another funny thing. Since our formula, 1/4 integral of n gamma phi r d phi dr. This is the average, you can think about it as the average number of intersections. With a random line. If I compute this for my line segment here, it's the same as if I had shifted my line segment down here, because a random line segment is the same as picking a random line segment up here versus shifting all of my random line segments. It's the same calculation. You just shift all of your line segments. Or you shift all of your random lines that you're counting the intersection number with. So I can shift it around. So I can shift. And because of this angle here, it doesn't matter how it's rotated. If I rotate my line segment, the average number of intersections with a random line doesn't change. So I could just put my line segment right here. And it's additive. So whatever I get for this line segment, I get some number out. And it's additive, and it's rotationally invariant, and it's translation invariant, and I can stitch them together. This formula is a constant times the length. The length is the only thing that is rotationally invariant, translation invariant, additive, and it gives you a positive measure. So it has to be the length. I'm trying to do this without calculus, and if you sit down and compute this constant, you actually find that it is the 1/4, and that's where the 1/4 comes from. The incredible thing about this is this doesn't just work with line segments. This works very generally, and the exact same proof works. The same proof idea works. So if I want to find, let's say I have some region E, and I pick a coordinate system, and I'll pick a vector, and that vector I'll pick a radius for, and it defines a plane. This plane will slice through my shape, and it will give me an area. Area of plane intersect E. Cool. We can do the same trick. It turns out that the integral, now how many planes are there? On the surface of a sphere, there are 2 dimensions of like how I can point. There are 2 variables. And then there's a third variable of how far I want to place this r here. So it's a triple integral. I'm kind of gearing this towards people who've done calculus 3. If I integrate the area now, instead of the intersection number, of P intersect E, over your random plane, I need some measure. I say measure. I need a way of picking a random plane, but let's say I can pick a random plane that is indifferent about rotation or translation. That's the only thing I need, just like what I needed with lines. Then this is a constant times the volume of E. And you can sit down and figure out what that volume is, or what that constant is. And this is the thing that we're going to need. And the next segment, we're going to prove Schlafli's formula. Let's put it all together. We have a polyhedra. So let me just keep it simple. I'll just write a cube. We have a cube, and it is a continuous differentiable family of polyhedra in R3. It has the same graph, but it's changing, the edge lengths are changing, the dihedral angles are changing. And I'm going to slice it up. Let's pick a point and a vector, and we will define a plane. This is our random plane P. And what it's going to do is it will slice up our shape, something like that. And let's call this P intersect XT. So let's zoom in on that shape. P intersect XT here might look something like this. At every vertex, it will have an interior angle, theta V. And we have our formula from before. 0 is the sum over the interior, over the vertices of the derivatives of theta V t dt, because, well, this is changing in time, so this is changing in time too, and we can take its derivatives. So all we need to do, the entire proof, is integrate over our random planes. What happens when we do that? So we'll take a triple integral over our randomly picked planes in R3. What does this do? Well, we're going to look at, let's focus on theta V of t. And we'll do this in 2 steps. The first thing that we'll do is let's zoom in on an edge in our polytope. Here's our point V. And this point V, let's focus in on all the planes that pass through that point V. All the planes that slice through V. So if we only integrate over, let's do this in 2 steps. Let's integrate over planes that pass through that point V of theta V t dp. So we're only doing like 2 integrals here now that we've picked a point that it has to pass through. It still can vary in a few different ways. Well, if we pick a ball around our edge, so let's pick a ball around our edge. So let me sketch this up here. If I have a ball centered at V around our edge, then our edge intersected with that ball is going to be like the wedge of a lemon. And we have our point V. And when we slice with this plane, what we're going to do is we're going to pick out a subsection of our wedge here. So let's actually start with a new sheet. That wedge, let's focus in on that wedge. So we have this wedge and our vertex V And what is our theta v at this particular time slice? This is proportional to the arc length of this dotted line here. The length of that is proportional to the angle that is right there. So what happens when we integrate over all of the planes that pass through the center of the sphere that we're focusing on of theta v t dp? When we average over all of these planes, what we're doing is we're averaging over all of those arc lengths. And so this here is a length, and Crofton's formula pops up. A different variation of it, where this will end up giving us something proportional to the area of that subsection of a circle. So it's the area of that part of the wedge. So it's that area. Well, the area here is proportional to the dihedral angle of that edge. And so what we get out of this is proportional to our dihedral angle. So let's bring back what we're actually integrating. We have a sum over the vertices, derivatives over t dt, and we want to integrate over all the planes, all of these random planes on both sides. So we get 0 on the left-hand side, and on the right-hand side we have, let's investigate the sum. We're summing over the vertices in each slice. So we have this slice of our solid, and the vertices here correspond to the different edges in our polytope or polyhedra. So really what we're doing is we're summing over the edges. So each one of these vertices belongs to one of the edges of our polyhedra, and we'll just identify those. We're going to integrate over the edge, the length of the edge, in terms of like picking out different vertices. And then we're going to integrate over our planes that pass through that fixed vertex. And we can take the derivative and pull the derivative out of the integral. So we'll pull the derivative out of this, and we get theta v of t dp, and then this integral along the edge is integrating over the vertices. Now we can apply our formula. Crofton's formula tells us that this is proportional to our dihedral angle of that edge. And then we integrate this. Let's just take this one step at a time. Replacing this with the dihedral angle, we have 0 is the sum over the edges, integral over the length of the edge of the derivative of the dihedral angle for that edge. And here we're integrating over the variable that's like each point. This is a point on each edge. And so this is equal to the sum over the edges over the length of the edge times the derivative of the dihedral angle. And that proves Schlafli's formula using Crofton's formula. Okay, so I think that's pretty cool. It's a really non-intuitive formula to try and prove, and to have such a slick proof is really cool. So I hope you enjoyed it. I think the math that we walked through is really incredible, and I hope you like this puzzle as well. And if you would really like to own one, go check it out on Canyon's store, and you can buy one for yourself. So take care, and hopefully I'll see you again soon.